Hi AP Chemistry. This is still Chapter 4. And Chapter 4, as I said before, is a very big chapter for the AP exam. This is going to be Section 7. This is going to be the last section of metathesis reactions. We'll test after this section and then go on to redox reactions. This section covers the stoichiometry involved in precipitate and neutralization reactions. We don't do gas producers. Couple of comments about moles versus millimoles. First off, please remember that molarity is calculated with moles of solute divided by liters of solution. And if we want to calculate the moles, we would just do moles equal to molarity times the volume in liters. And that's fine. That's the way we're used to. That's the traditional way. We could also use millimoles, and it would just be that millimoles would be equal to molarity times the volume in milliliters. There are two advantages to using millimoles. Advantage number one, you don't have to convert your volume to liters. And advantage number two, it'll give you large numbers. It's just a comfort issue. I am going to do examples both in the moles and the millimoles. Alright, a couple of suggestions for doing stoichiometry problems. Most of the time they're very long, they're multi-step, and they're very hard. The brackets indicate concentration. You will be doing two types, precipitate and neutralization. If it's a precipitate problem, chances are they're looking for the mass of the solid. If it's a neutralization problem, they're just looking for the concentration of the water or the excess ion or the weak acid or any such thing like that. Most of your stoichiometry for solution solving is going to be limiting excess problems. Always do the stoichiometry problems in moles or millimoles, not molarity, because the volume changes. Keep in mind every problem's different, and millimoles or moles, I'm going to do them both ways, a little in moles, a little in millimoles, so find your comfort. Here's our first example. We are going to calculate the mass of sodium chloride that must be used to make a solution that will precipitate out all the silver ions from 1.5 liters of a 0.01 molar silver nitrate solution. So here's basically what it's talking about. It has, in a beaker, let's make this easy, a certain number of silver ions. Silver nitrate is a soluble salt, dissociates 100%. So here's a picture. You need chloride ions to go in here and precipitate out all the silver ions. Visually, how many chloride ions would you need to precipitate out the 3 silver ions? Well, you'd need 3 chloride ions. Done. Alright, so there's a model of this type of problem. So here we go. First thing I'm going to do is I'm going to write out the reactants. It says sodium chloride and silver nitrate. Both are soluble salts. I am going to predict the product. This is a metathesis reaction, otherwise known as double replacement. Based on solubility rules, sodium nitrate is going to be the aqueous portion. These are going to be your spectator ions. They are going to be in solution, but they do not do anything. Chlorides are soluble except for silver, mercury, and lead, which are insolubles. This is silver, so this is my precipitate. Balance it. It's all balanced, so you don't need to do anything more. This question is not a limiting excess. It is not asking me about the quantity of the product. It is asking me how much sodium chloride do I need to get rid of all the sodium, I beg your pardon, all the silver nitrate. So this is just a stoichiometry. So the first thing I'm going to do is I am going to convert the silver nitrate to moles. And moles is equal to molarity times volume. in liters. This one I'm going to do in liters. So I have molarity of 0.0100 0.0100, yep, and I have 1.5 liters. So I have 0.0150 moles of the silver nitrate. And I also have 0.0150 moles of the silver and 0.015 moles of the nitrate, which nitrate's going to be the spectator ion. The question's asking you what mass of sodium chloride is used to precipitate out all the silver ions. Well, this is the stoichiometry part. I have 0.0150 moles of the silver nitrate. According to the balanced chemical equation, it's a 1-to-1 ratio. And since it's asking me for mass, I need to convert moles of sodium chloride to mass, so I am going to put in my molar mass ratio right off the bat instead of doing it in 2 steps. My answer should be 3 sig figs. So I need 8.77 grams of sodium chloride. I need to place that into solution, and that will be precipitating out all the silver if it gets mixed together. This one's a little harder. This one is going to be a limiting excess problem. We are going to do all the bells and whistles. We are going to figure out the theoretical yield of the solid, and then we are going to figure out all the concentrations of the species in the solution after it's mixed together. So first thing I'm going to do, I'm going to write out the reaction according to the question. Here are my 2 reactants written appropriately. Both of them are in solution, just like the problem says. I am going to predict the products by double replacement reaction. Then I'm going to predict which of the products is the solid. Sodium, anything attached to sodium according to solubility rules is soluble, so this guy is an aqueous. That leaves him to be the solid, the precipitate. Sulfates are soluble except for group 2A, and so that is my solid. Balance it. I need a 2 here. The information given I'm going to write down. They tell me I have 10 mils of a 0.250 molar of that and 10 mils of a 0.350 molar of that. And before I even mix them together, let's do a little analysis. This is in a separate container. According to logic, I have 0.00250 moles of the barium chloride. Moles is equal to molarity. Molarity times volume gives me this moles of barium chloride. From the compound, the formula of the compound, I have floating in the solution before I mix it, and the chloride is one of the spectator ions, but for every 1 mole of compound I have 2 moles of the chloride ion. And I'm going to do the same thing for the sodium sulfate. For every 1 mole of the compound I have 2 moles of the sodium. So I have 0.00350 moles of the compound. That means I have 0.00700 moles of the sodium ion, which is your other spectator. Metathesis reactions is really the story of 4 ions. 2 of them will form a precipitate or water or gas, and 2 of them will be spectator ions. In this situation, the sodium and the chloride will be your spectator ions, because the formula of the precipitate is the barium sulfate. Alright, so here's all the information before I even start anything. This is before mixing. Then I mix them together. So now I have a limiting excess problem. When I mix them together, I have to figure out which one of these compounds here, these are 2 reactants, which one will form the least amount of precipitate. Right here I'm going to do stoichiometry from my balanced chemical equation. It's all 1-to-1 ratios. For every 1 mole of barium sulfate, I need 1 mole of barium chloride. For every 1 mole of barium sulfate, I need 1 mole of the sodium sulfate. 1 mole of the sulfate. It's a 1-to-1 ratio. Of the 2 answers, this one is the least amount of precipitate. That means this ion in this compound is my limiting. That means this ion in this compound will be my excess. I need to know the theoretical yield of the precipitate, and my precipitate is, of course, the barium sulfate. I have 0.00250 moles of the barium sulfate. Multiply that by molar mass. 1 barium, 1 sulfate, 4 oxygens. 1 mole of barium sulfate is 233.37 grams. I have 0.00250 moles of it, and I get a theoretical yield of 0.583 grams of barium sulfate. That means after I mix it together, if I were to separate the solution from the precipitate, dry it out, I theoretically should have 0.583 grams. This is the theoretical yield of my solid. Next, what I'm going to focus on next is my excess reactant. Which is the sodium sulfate. 2 steps. First, I am going to calculate how much sodium sulfate did I use to make the 0.00250 moles of the precipitate. Remember, this is my least amount. Least amount of product is 0.00250 moles of the barium sulfate. I am going to do stoichiometry, and I am going to figure out how many moles of the sodium sulfate did I use to make that amount of barium sulfate. According to the balanced chemical equation, it's a 1-to-1 ratio. So I used 0.00250 moles of the sodium sulfate. and this is what I used. All right, second step. How much is left over? I had, let's see, where is it? The sodium sulfate, I have 0.00350 before the reaction. I used 0.00250 moles of it to make the precipitate. The difference between those two numbers is 0.0010 moles. And that's the amount left over. That's the number of moles left over in the solution. All right. So then what we're going to do now is I'm going to calculate the concentration, which I'm going to indicate with brackets, of all species in solution. Well, one of them is very simple. The barium of the barium chloride has been all used up. It was my limiting, so it's gone. The chloride ion of the barium chloride is a spectator. According to my calculations on the previous slide, I have 0.00500 moles of the chloride ion in the total volume added together in liters of 0.0200 liters, and that gives me the concentration of the chloride ions of 0.250 molar. Notice the volume. We've poured the two 10 mils together. Now I'm going to do the other two species in the same manner. My sodium ions, here's my second spectator, according to the math that I did. And notice it's the same volume. These two guys are doing absolutely nothing. They are just floating around in solution. And then my excess. According to what I just calculated here, I have 0.0010 moles of the sulfate left over in the 20 mils, or the 0.0200 liters. I'm not focusing on the sodium because it is a spectator ion. It was not used to form the precipitate, so I'm not even taking that into consideration at this problem for this one. I am just focusing on the sulfate, and that gives me 0.0500 molar. Here's another example. It's pretty similar to the last in the sense that it is a precipitate problem. It is a limiting excess problem. 50 mils of sodium phosphate, 50 mils of copper 2 chloride, and we're going to do pretty much the same type of math. So the first thing I'm going to do is I'm going to write down my reactants. You have to know your ions. It says it's a solution. Copper 2 chloride, a transition metal. The 2 tells you what charge for the chloride. Predict your products. This is a precipitate reaction, not a neutralization. One of these is a precipitate. I know it's not this guy. Anything attached with sodium, without exception, will always be completely soluble. That means that this guy is my solid, which correlates to the solubility rules. Phosphates are insoluble except for group 1A or ammonium. Copper is neither group 1A or ammonium, so this is insoluble / slightly soluble. Balance it. I need a 3 here and a 2 there, and then that gives me a 6 there. So this one's going to have coefficients. The last one didn't have the coefficients like this. It was all 1 to 1. I'm going to do the same idea. I'm going to write down my info. So it gives me, that's the information they gave me in the problem. Take the volume in liters, multiply it by the molarity, and you get 0.00500 moles of the compound. Now, just logical thought, this is before mixing. If you have 0.00500 moles of the compound, and the sodium ion is a 3 to 1 ratio to the compound, that means you are going to have 0.00150 moles of the sodium ion, which is a spectator, obviously, and you will have 0.00500 moles of the phosphate ion, which is responsible for the precipitate. And I'm going to do the same thing for the copper 2 chloride. Change the volume to liters, multiply it by the 0.1, and you will have 0.00500 moles of the compound. Copper ion, it's a 1 to 1 ratio. For every 1 mole of the compound, you got 1 mole of copper. I have 0.005 moles of the compound, so I have 0.005 moles of the copper ion. I have 0.005 moles of the compound, and it's a 2 to 1 ratio for the chloride, so that's doubled. So for every 0.00500 mole of the compound, you have 0.010 moles of the chloride, which is the other spectator ion. And this is before mixing. This is my information. What I'm going to do now is my limiting excess problem, and I have 0.00500 moles of compound number 1, which is the sodium phosphate, and I have 0.00500 moles of reactant number 2, which is the copper chloride. What I'm going to do here is I'm going to figure out which one of these reactants makes the least amount. Again, this is my method. This is what I'm comfortable with. There is another way to do it, but I don't do it that way. I do it this way. If you have a different way, that's fine. You have to show all your work, and you have to come up with the right answer. According to the balanced chemical equation, for every 1 mole of copper phosphate, I need 2 moles of sodium phosphate. For every 1 mole of the copper phosphate, I need 3 moles of the copper chloride. And just kind of look at it. Notice this 2 kind of correlates to this 2, and this 3 kind of correlates to this 3. In order to make copper phosphate, you need 3 coppers and 2 phosphates. So it kind of goes together. Do the math. This guy will produce of the copper phosphate, the product, the precipitate, and this guy will produce notice that this is my least amount. That means that the copper in this compound is my limiting reactant. The chloride is a spectator. That means that the phosphate in this reactant is in excess. The sodium is a spectator. The 0.00150 moles of sodium does nothing but swim around. Convert the 0.00167 moles of copper 2 phosphate to mass using molar mass. And you get a theoretical yield of 0.636 grams of the precipitate, which is copper 2 phosphate. That is theoretical yield, and that is the mass of precipitate. The next step is to focus on the excess reactant, which is the sodium phosphate. Again, it's actually the phosphate ion. First step, how much sodium phosphate did I use to make the 0.00167 moles of precipitate? I'm going to do stoichiometry, and it's 2 moles of the sodium phosphate needed for every 1 mole of the copper phosphate solid. And I do that math. And again, look at it intuitively, 0.00334 moles of phosphate ion. Again, the sodium is still just a spectator ion. Step number 2, I had, let's go back, I have 0.005 moles of sodium phosphate. According to step number 1, I used 0.00334 moles of it to make the precipitate. That is going to leave behind 0.00166 moles of the sodium phosphate, actually more the phosphate than the sodium. That's going to leave behind the 0.0016 moles of the sodium phosphate. Again, the sodium is a spectator. This number applies actually only to the phosphate, because the phosphate is responsible for the precipitate, not the sodium. Alright, now concentrations of all the substances, and I'm going to start with the easiest one, brackets mean concentration. The limiting ion was the copper, so the copper 2 is gone, so I'm going to do that the easiest one. It's 0. The chloride, we go back and look for, this is the spectator ion, the chloride ions is 0.01 moles. It is a spectator. It is not doing anything. I have 0.01 moles before I mix, 0.01 moles after I mix, because it's a spectator ion. So I have 0.010 moles. Total volume, I mixed 50 and 50. That's 100 mils. That's 0.1 liters. And my concentration for the chloride ion is 0.100. Concentration for the other spectator, I have 0.001 0.00150 moles of sodium before mixing. The sodium was not responsible for the precipitate, so I have 0.00150 after mixing, and it's 100 mils in liters, 0.1. The concentration of the sodium ion after mixing, and my last species is my phosphate. That is my limiting ion, and according to above, I have 0.00166 moles of it left over in my volume of 0.1000 liters, and that gives me a phosphate concentration of 0.0166 molar. Example number 4, we are going to do this in the second part. That's the end of part 1.